Talk about covariance and correlation coefficient. So covariance, first we have to define the covariance of two variables in a sample. So what we have here is 1 over n minus 1. And we talk about n, we talk about the sample size. Okay? We subtract 1. Usually in statistics, we subtract 1 to get rid of any error in that sample. Because again, we're not using the population. So the sample could be overestimating or underestimating. And then what we do is we find the difference between every single x and every single y point in the form x comma y. And we find the difference between that x and the average of the x's, and that y and the average of the y's. So we call this x bar. There's just like a bar on top of it. And x bar is the mean, the average of the x's, and y bar is the mean or the average of the y's. So the covariance is the measure of how closely related the change in one variable is related to the change in the other variable. Okay, so if you think about it, when we're looking at a scatter plot, we want to know as x increases this much, y increases this much, right? So how closely related that changes to one another. Now, correlation coefficient is a very, very long equation. I'll show you how to set it up. Set it up in a chart, very, very easy. I'm also going to show you how to solve the correlation coefficient on Excel, which takes just moments. Okay, so if we take a look at this, n is like the number of terms, number of data points in the sample, and then we just have the x and the y. So when we're actually looking at like a table of values, if we have x and y, the x's are literally just the x's and the y's are just the y's. When we see this here, this is just a Riemann sum. So this is the sum of all the xy's, and I'll get into that in just a moment. This just means sum, of course, is just addition. So we're going to add maybe every single x value, 1, 2, 3, 4, 5, all the way down, or every single y value, or every single x times y value. But I'll get into that. Okay, so when we talk about the correlation coefficient, what this number does is it gives us like that number measure, that quantitative measure of the strength of the linear correlation. So we saw in the previous examples, this page right here, we just took a guess, like, oh, that looks pretty strong, that looks pretty moderate, right? But now what we're going to do is we're going to actually assign a number value to this. So all the values for a correlation coefficient range between -1 and 1. And what this means is basically from -1 to 0, this is the negative correlation. This means that the line is moving down, okay? And from 0 all the way to 1, this means that it's going up. At 0, this just means no correlation. Okay, so a perfect positive linear correlation is one where the dependent variable y is directly proportional to the changes in the independent variable. Okay, and in this, of course, the line is a perfect line. We're going to get it in the form like y equals, in grade 9, you would see y equals mx plus b, but now we see y equals ax plus b. Okay, and the exact same thing when r equals -1, it's a perfect negative correlation. And sorry, I should say when r equals 1, it's a perfect positive linear correlation. Now, it's so important to note this. So note, as n approaches infinity, so when we talk about n, we talk about the number of data. As n approaches infinity, so the number of data gets bigger and bigger, the correlation coefficient improves accuracy. So the more times you do an experiment, the more accuracy you're going to have. And here is the chart. So for two variables with no linear correlation with no linear, I'll just move this right to this side, correlation or little correlation, the correlation is close to 0. Now, here we go. This is broken down into thirds. So up into a third, let's go green. Green's dark. Up to a third, so negative a third or positive third, this is going to be called weak. Now between 1/3 and 2/3, either negative or positive, this is going to be the area where it's moderate. And between 2/3 and 1, this is going to be a strong correlation coefficient. So now let's do a couple examples.